All right, this is a recorded lecture for uh, Principles of Biology 110. We're going to introduce Chapter 2 and talk a little bit about essential chemistry for biology. We'll talk about matter, atoms, the subatomic particles, protons, neutrons, and particularly electrons. We'll describe chemical bonds and talk about water. So chemistry is really the study of matter, any solid, liquid, or gas, anything. Um, and there are thousands and thousands of chemical compounds where we're going to look at the basic materials that make up the atoms, and they are particular types of the smallest parts of these chemical compounds. We're not going to be chemists, though. We're not doing chemistry. We're not going to memorize chemical equations or solve for various uh, constants or uh, anything like that. We're just talking about kind of a basic understanding of what is chemistry and the different properties of chemicals. Lots of people struggle with chemistry. It's very abstract, but everybody is familiar with chemicals. They're not dangerous things. They're just part of what's around us. We're we're like I've said, we're going to just kind of get an overview of it. Chemistry is very important in biology. A lot of times when we're trying to understand something in biology, it gets down to chemistry. But biologists are not chemists. We're not doing what they do. We usually work with chemists. We don't replace them. So we're different groups. Um, and we often collaborate with chemists and work together. Okay. So out of all these different types of chemical compounds, we can chemically simplify them into individual types of matter called elements. Um, Using means like fire or electricity, we can break compounds down to about 90 some naturally occurring elements. Each one of these elements is composed of different types of atoms. The atoms themselves are made up of these small particles called subatomic particles. Atoms have protons in their center at the nucleus. It's a positively charged particle with some mass. They may or may not have also neutrons there, which are neutrally charged or not charged particles that have mass right in the center in the nucleus. And then outside of the nucleus are electrons, and they move around the central area, the nucleus, in orbitals, and the electrons are very, very small but have negative charges. Okay, and so these are two different types of atoms, a hydrogen atom, which has one proton, and then an oxygen atom, which has 8 protons. In uncharged atoms, the number of protons equals number of electrons. So they can appear like that. Here's a closer view. This would be a helium atom because it has 2 protons, okay, and then its uncharged state, it would have 2 electrons orbiting around it. So there's lots of different types of atoms. They're here shown in the periodic table. I show this to you because it's in the chapter, but we're not going to memorize this. We're not going to memorize all the information on this, but it's just to show you the different types. Okay, we'll talk a lot about several different types of atoms. Hydrogen atoms, which have 1 proton. Carbon atoms, which have 6. They're represented by the letter C. Nitrogen atoms, which have 7 protons. And oxygen atoms, which have 8 protons. Okay, those are the basic uh, atoms that make up most of the human body. There's lots of other ones, but those are by far the most numerous. Okay, so what determines the composition or the type of atom is the number of protons. The number of neutrons can vary. When the number of neutrons varies, we refer to those atoms as isotopes. And so here are 3 isotopes of carbon. Carbon 12, which has 6 neutrons, carbon 13, which has 7 neutrons, and carbon 14, which has 8 neutrons. Okay, these different isotopes act pretty much in the same way chemically, but they weigh slightly different amounts. And sometimes some of them decay. They will actually radioactively give off uh, a particle to change their identity. Isotopes are useful in that they can be used, the rate which radioactive isotopes decay can be used to date things. And so uh, here carbon uh, cosmic rays convert nitrogen to carbon-14 at a steady rate. And so in the environment, we know that that occurs in a certain amount. But once those carbons are incorporated into organic material, they'll decay back into nitrogen. And so the rate at which that happens is steady, and we can use that to date bones. The other thing that can vary is electrons. And when electrons vary, that changes the charge of an atom. And so here we see Na stands for sodium. A sodium atom can give up an electron to become positively charged. And I think the other one there is chlorine. Chlorine can take an electron, and when it takes an extra electron, it gains a negative charge. And these charged atoms are referred to as ions. Okay, and they're perfectly stable that way. In fact, many times atoms would prefer to gain or lose electrons to fill or empty an orbital. And this is what causes chemical bonding. These outer electrons, which are sometimes known as valence electrons, uh, can be actually make atoms more stable when they give up or take or share electrons. And this is what causes chemical bonding. And the transfer of electrons is a type of bond called ionic bonding. And then the positive charged atom and the negatively charged atom will be attracted to one another. Okay. Other times, atoms share electrons. And this sharing of electrons is referred to as covalent bonding. And here the electron moves around two different atoms, around the nuclei of two atoms, and this produces a very tightly held arrangement of atoms. Water molecules have two hydrogen ions or two hydrogen atoms and two oxygen atoms that are sharing, or one oxygen atom sharing electrons. Carbon shares 4 electrons with 4 hydrogen atoms, and oxygen can share 2 electrons with another oxygen. And so these are covalently bonded substances, formed when 2 or more atoms share valence electrons. Neither atom gains a charge, but because the atoms have partially filled, orbitals, this is very stable. And the strength of the covalent bonds depends upon the number of electrons shared. Okay, the more electrons shared, the stronger the bond. And so a single bond is shown on top with 2 hydrogen atoms sharing 2 electrons. Then a double bond is shown in the center with 2 oxygen atoms sharing 4 electrons. And then a triple bond is shown in the bottom. Okay. One compound that we'll talk about a lot is water. Water is oxygen and 2 hydrogen atoms sharing electrons, but they don't share them equally. They're called polar covalent bonds because the electrons spend more time near the oxygen atom, and so that becomes the negative pole, and they spend less time by the hydrogen atoms, which become positive poles. So it's like a magnet. Okay, then the positive and negative regions of different oxygen atoms are attracted to one another, and this is called hydrogen bonds. And this is what gives water its unusual properties. It remains a liquid at a vast range of temperature. It takes a lot of heat to evaporate it, so it's good at storing heat. It's also good at dissolving ionic substances and has a lot of surface tension, so it's kind of interesting. So these hydrogen bonds then are weak attractions between two different molecules. Okay, and that's what gives water its properties, and those properties include cohesion, attraction to other atoms, the surface tension. This is all due to these hydrogen bonds. And our bodies and most cells are mostly made of water. We're about 65% water. And water is found in all living organisms, and it's abundant. It's tied to life. It's the single most common substance in all living organisms, and it's because of these weak chemical bonds. And so water has this high specific heat. It has a high heat of vaporization. It's um, it's in a liquid form. It's more dense than in a solid form, so that even when it gets cold, ice forms on top, and that traps the heat in the bottom, so it doesn't freeze easily. Water's an excellent solvent, dissolving other polar molecules and ions, and it can organize nonpolar molecules to form structures. So water is really unique, and it forms ions on its own, and so it can form hydrogen and hydroxide ions, so it's really useful in chemical reactions. Okay. One practical application is that water is useful for identifying where life might be present. Okay, lots of times we think of life and we think of these cartoons or special monsters, but it's more likely that we're looking for chemistry and we'll find microorganisms before we find anything that looks like this. And so the search for life on other planets is really the search for water. And we look for indications of water now and indications of water in the past, like minerals that form in water or sedimentary features. So on Mars or in other places in the solar system, we are basically looking for water. Okay, I'll stop there, talk more about this in lecture, and talk about some further applications of chemistry.